Hello.
Yes, sir. Yes, sir.
Yeah, is it audible?
Yes, sir. You are audible.
Yeah, yeah, we can start.
What's your name? Ma'am, should we start? Hello. Ma'am.
Yeah, Archana ji will start the session.
Yes. Sir, wait a minute. Ma'am is not there, I guess. She
Yes,
will
yes,
connect
yes.
you.
Okay, dear participants, Dr. Chinna Rajaram is with us now, so we are good to go. And just to brief you with, he was my colleague at Triple IT Hyderabad and very passionate researcher, we can say, in earthquake engineering area. His work is exceptional, and it's a really honor to invite him on this stage to learn from him. Now I'm requesting our students, please move ahead. Kindly introduce Dr. Chinna Rajaram for
Yes,
this
ma'am.
particular session.
Yeah.
Sir is ready now.
Okay. Good afternoon, everyone. Ma'am, am I audible?
Yes, yes, you are audible.
Yes, you are
Yes.
audible.
Okay. Yeah, okay. Good afternoon, everyone. It is my pleasure to welcome you all here today. I hope this day finds you well and filled with
Darpita
enthusiasm.
Mahima,
Sorry, ma'am. Should I continue? Hello, ma'am. Okay, I'm continuing. As we gather here for today's
Omkar,
expert session,
Yes, ma'am.
Omkar, are you there?
Yes, ma'am. Yes, I'm there.
Darpita, not able to hear you. Are you there?
yes, ma'am, we are here only.
She is audible.
Let us not delay the session. We are wasting time.
Good afternoon, everyone. It's my pleasure to welcome you all here today. I hope this day finds you well and filled with enthusiasm. As we gather here for our expert session, thank you for joining us and taking the time to be part of the session. Although we may be meeting virtually, the purpose of today's event remains the same: to connect,
Omkar,
to learn, and to share
I can't hear
unique
anyone.
ideas.
Yeah, are you guys there?
Yes, ma'am.
Darpika, kindly introduce Professor Chenna Rajaram.
Madam, actually, she is audible, ma'am. She is continuing it. I think
I guess,
there
ma'am,
is
you
some
should.
problem.
Okay. Although we may be meeting virtually, the purpose of today's event remains the same: to connect, to learn, and to share meaningful ideas. These platforms also allows us to bring together diverse voice and perspective, making today's gathering both special and impactful. Moving further, it is my honor to introduce today's expert, Dr. Chena Rajaram.
Okay.
He did Bachelor's of
So
Technology.
it's my pleasure to welcome Dr. Chenna Rajaram on this platform. So let me introduce Dr. Chenna Rajaram did his Bachelor of Technology from Sri Krishna Devaraya University. He holds a PhD and Master of Science by Research from IIIT Hyderabad, specializing in earthquake engineering. Currently, he is working as an associate professor at Rajiv Gandhi Memorial College of Engineering and Technology, Nandia. He has published 45 journal papers and 35 conference papers, including 30 WS indexed publications, and serves as a reviewer for leading international journals such as Natural Hazards, Soil Dynamics, and Earthquake Engineering and Engineering Vibrations, Current Science, and Computers and Structures Journals, etc. He is also one of the editorial member for the most cited journal, World Scientific Reports. He has conducted several short courses on earthquake resistant design of buildings for both UG and PG students and encouraged them to do research. He has guided 40 UG students and 16 PG students and one PhD student. His spanning strong ground motion simulation, seismic risk assessment, applied element method, and machine learning applications in earthquake engineering. He is a recipient of multiple honors, including the Best Teacher Award in 2024, Best Researcher Award 2024 and 25, the Vista Young Faculty Award 2021, and Combination Certificate from Embassy of Islamic Republic of Afghanistan 2016. He has conducted and organized several short courses, FDPs, and international webinars, and regularly delivers invited lectures on earthquake engineering and disaster mitigation. Personally, I have seen how Professor Rajaram worked in a research field. His work is excellent, and it's really honor to have him on this platform. I welcome you, Dr. Chinna Rajaram. Now the platform is yours. You can please start your presentation. Thank you, sir.
Yeah, thank you, Dr. Archana ji. And sharing my screen. So is it audible?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
So is my screen visible?
Yes, sir.
Yeah. Thank you, Dr. Archana ji and Vidyavan College of Engineering and Technology, Mumbai. So today I'm going to, without any delay, I'm just giving the lecture on determination of seismic pressure by equivalent static method as per IS 1893 2025. So the contents of this today's presentation is introduction, equivalent static method. Under equivalent static method, earthquake zone factors, importance factor, design spectra, site classes, approximate fundamental natural period, elastic force reduction factors, and seismic weight calculations for the calculating design base shear using equivalent static method, and design horizontal base shear, and how the design horizontal base shear is getting distributed onto the floors, and how to calculate design base shear in vertical direction, and how it is getting distributed into the vertical members. So these are the contents that are going to be delivered in today's presentation. Coming to the introduction, before going to discuss about the equivalent static method, so first of all, we should discuss about what is the earthquake design philosophy of IS 1893. So, as per IS 1893, the design philosophy is for minor shaking, the main members should not get damaged, like beam elements and column elements. And the building parts that do not carry load may sustain repairable damage. And for moderate shaking, the main members may sustain repairable damage, and under strong shaking, main members may sustain severe damage but should not collapse. So the main objective and motto of the design philosophy of IS 1893 is the building should not get collapsed, even though the like severe cracks or severe damage may take place, but building should not get collapsed under any kind of shaking, like moderate or strong shaking. And it is a fundamental safety concept. Safety is very, very important in earthquake design philosophy that governs how a structure is expected to behave under loads. Yeah, so generally there is a contradiction between earthquake resistant and earthquake proof. Now, what is the difference between these two? So definitely there is a difference between earthquake resistant and earthquake proof. So when we talk about earthquake resistant, so the main objective is life safety. So it prevents the catastrophic collapse and allowing people to evacuate safely. So this is what is the earthquake resistant design. And earthquake proof means it is the main objective or the main goal of earthquake proof is it is a zero damage, which is not possible. So during any kind of shaking, or even minor shaking or moderate shaking or severe shaking, there should be some kind of damage takes place in the building itself. So that's why zero damage is not possible in a building during the shaking of the ground. So that's why this is earthquake proof design, not earthquake resistant design, and it aims to withstand any earthquakes without any structural harm. And the design philosophy is it bends, don't break. And here in earthquake proof, so the main philosophy is it eliminates all seismic events. And what are the methods for earthquake resistant design so that the damage can be reduced? So the methods are provide ductility in the structure in terms of reinforcement as per 3920, like ductility, dampers. Even there are various types of dampers like passive dampers and active dampers, liquid dampers. So these guys absorb the energy. And base isolation, this is also one of the techniques to reduce the damage of the structure. And steel reinforcement concrete, it provides the strength of the structure. And coming to the earthquake proof, so it is very, very difficult providing massive energy absorption. So as you know that huge amount of energy is getting uh, coming during the earthquakes. So to absorb that kind of energy is very, very difficult. So and providing this massive energy absorption is highly difficult. And highly advanced isolation, which is not only the structures which are constructed, it should be earthquake resistant structures and it should not be earthquake proof structures. And what are the various methods in earthquake analysis? So the method of analysis shall be linear for the earthquake resistant design of structures, which can performed by the following methods. The first one is a static analysis by equivalent static method. So basically there are two types of methods. One is static analysis, the other one is dynamic analysis. So for static analysis, the method we follow is earthquake static method. There are two methods. One is a response spectrum method, the other one is response history method. So previously, this response history method is termed as the earthquake static method. And response history method is basically dynamic analysis method. Now the next question is, so when do we go for linear equivalent static method? And what is linear equivalent static method? A method of linear analysis of a structure to estimate the dynamic earthquake response, considering the fundamental lateral mode of oscillation using the pseudospectral acceleration response spectrum of the design earthquake hazard. Now, what are the terminologies in the definition of linear equivalent static method? So, excuse me. So, we'll discuss one by one. Now, when do we apply this equivalent static method? So, the equivalent static method is generally applicable as per IS 1893-2025 is the fundamental natural period. There is a mode 80% of the mode participation, more than 80% of the mode participation in translatory direction. So then only this equivalent static method is applicable. So if not, then we will not go for equivalent static method. Okay. So if in the previous code, that is 1893-2016 code, so there are guidelines based on the height of the building, based on the zone. It is classified that we have to go for equivalent static analysis in these kind of consideration. Consideration is completely different. And coming to the earthquake zones, so we'll discuss the earthquake zone part and building categories and building configurations. So building categories basically will divide it into special structures, normal structures, like important structures. That kind of categories there. We'll discuss each one of them. And the building configurations, like any kind of building configuration, whether it is the structure is a regular structure or irregular structure, so we have to go with the equivalent static method as per the current code. And response spectrum method, which is a dynamic analysis, and irrespective of the zone, irrespective of the building category, we have to perform response spectrum method. And building configuration recommended for irregular buildings. Okay, so the response spectrum method is recommended for irregular buildings. And there is another method called a response history method, which is a time history method. So it is applicable for all zones and building category recommended for critical and special buildings, except for critical and special small buildings. Now, what is the definition of small buildings? So, the definition of small building is given here. So, in single story residential building with less than 15 meters square of the built up area. So, for a single story structure, if the built up area is less than 50 meters square, with load bearing walls oriented along both principal plane directions to minimize the torsional irregularity and structural plan density not less than 15% and laterally supported wall lengths not more than 3 meters. So for these kind of categories, so it is termed as a small building according to the latest code of IS 1893. And building configurations recommended for all irregular buildings. Now here in the earlier version of 1893, we use only maybe one ground motion or two ground motions to obtain the response of the structure, and we don't know what are the characteristics of the ground motion itself. Now here, as per the response system method in the latest code, so we have to perform 30 ground motions. So we cannot perform only 29 ground motion or only 28 ground motion. There is no relaxation in that. So if you study those who are doing response history method, so they have to perform 30 ground motion records itself. And what is the equivalent static method procedure? So what are the various steps involved in that? So here a pictorial representation is given for equivalent static method. So the first step is, so when do we use this equivalent static method? So it is clearly given for structures. So where the first translation mode of oscillation governs the primary earthquake response. So what is the governing parameter is the mode shape. That is the 80% of the mass participation is there in the first mode. So then we go for equivalent static method. And second step is prepare the analytical model. So we have to prepare the analytical model using the like any kind of software, that kind of thing, and apply gravity loads. So as we know, dead loads, live loads, and etc. other loads. So apply those gravity loads onto the structure, and then perform the earthquake load. That's the apply the lateral load. That is earthquake loads. Then combination of load. So as per the 1893, the load combinations are given. So like 1.2 times of dead load plus 1.2 times of live load plus earthquake load in x direction, y direction, like that. So there are various cases which are given in IS 1893. So we have to perform all the load cases onto the structure. Then after that, extract the structural response. So after performing, applying the combination of the loads, then we get the response of the structure. So that we have to extract. Then after that, we go for the design of the structure. Then next one is the revision of the codes. The Inner Standards of ICT 93 was initially published in 1962, titled Recommendations for Earthquake Resistant Design of Structures. So from 1962, the first code was drafted, and after that, the first revision takes place in 1966. And followed by 1970, 1975, 1984, then 2002, 2016, and 2025. Now, if you see from 1984, there is a lot of gap between these revisions, from fourth revision to fifth revision to sixth to seven revisions. But if you see before 1984, so max hardly 5 years one revision takes place. Okay, from 2002 onwards, since 1966 to 1984, the earthquake code is a single code, and from 2002 onwards, there are parts are come part 1, part 2, part 3. Part 1 is for buildings, part 2 is for industrial structures, like that the categories are given. Okay, and we'll see what are the various categories that are there in 2025 and 2016. So in 2016, there are five parts. Part 1 is related to general provisions of the building, general provisions related to the hazard, and part 2 is related to the liquid retaining structures, that is the liquid storage tanks, and part 3 is for bridges and retaining walls. Part 4 is for industrial structures, and part 5 is for base isolation buildings. And in 2025, more number of parts are coming with various kinds of structures. So for part 1, it is general provisions similar to 2016. Part 2 is for liquid retaining structures. Part 3 is for bridges. Part 4 for industrial structures. 5 for buildings, 6 for base isolation, 7 for long distance pipelines, 8 is for steel towers, and 9 is coastal structures, 10 tunnels, 11 are earth and embankments. Out of these 11 parts, few parts of the 1893 are released, and few more are under review. Now, what is the equation to be used for calculating the equivalent static method? There is an earthquake horizontal force, that is VBDH, at the base of the structure, and there is an earthquake vertical force, that is VBDV, at the base of the structure, considering the pseudo-spectral acceleration spectrum shall be estimated as. So this is what is the equation. So in the 2016 code, we use the equation Z by 2, I by R, and SA by G is the equation for calculating the AH value, that is the horizontal seismic coefficient. But here, there is no term called 2. Okay, so why we will discuss in subsequent slides. So VBDH is equal to AHD into W, where W is the seismic weight, and AHD is the horizontal design horizontal seismic coefficient. Similarly, in vertical direction also. Now coming to the earthquake zone factor. So the value of the peak ground acceleration divided by acceleration due to gravity, that is SA by G, to be considered towards the estimation of the effects of design earthquake shaking on the structure, corresponding to the return period and the earthquake zone in which the structure is located. So in the previous code, if you observe, the earthquake zone factors are only four for four zones: zone 2, zone 3, zone 4, and zone 5. Earlier it was only four zones: 2, 3, 4, 5. And the factors are 0.1, 0.15, 0.1, 0.16, 0.24, and 0.36. So that means the maximum playground acceleration for zone 5 is 0.36. But here, the return period, that is very, very important fact parameter, came in IS 1893 or 2025. So these return periods are given like this: 75 to 9,995. So these return periods how we calculate these written periods. I will give one example in the subsequent slides. And the earlier code, if you observe, the design basis earthquake is for 475 years for normal buildings. Okay, and here the 2700 and 2475 years is a written period for buildings. Okay, so the buildings are categorized in the earlier code. The buildings are not categorized based on the functional utility. It is given as the importance factor. Importance factor for normal buildings, the importance factor is 1. For hospitals, that kind of structures, the importance factor is 1.2, and for special structures, it is given as 1.5. But here, the buildings itself are classified. So how it is classified, and I show. So we'll see what is the return period, and some simple calculation is given here. So what is return period? The return period or recurrence interval of an earthquake is the estimated average time between events of the specific intensity of the magnitude occurring at a given location. So for a given location, excuse me. So what is the return period of an earthquake that has 2% probability that exceeds in 50 years? Assuming that the design life of the structure is say 50 years. So for that, what is the 2% probability of occurring return period of an earthquake? So we can use the equation, that is Pn is equal to 1 minus 1 by t whole to the power of n. So where n is the design life of the building, that is the 50 years, and from that the probability is 0.2%, means 0.02. So by simplifying this equation to obtain t is equal to, it is approximately equal to 2475 years. So this is how we generally calculate the return period. Say 1% probability is around 9975 years. Sir, 9,975 years, which is given here. That is 9,975 years. So yeah. So coming to the return periods, based on the return periods, these return periods are assigned to the structures. So earlier it was the concept of return period was not there, but whatever the spectrum that we see in the earlier code, so that is for 2,475 years return period. So that is for 2% probability of the structure. Okay. Now here the return periods are assigned to the structure. So normal structures, important structures, critical structures, and special structures. So these are the categories that are given in the current code. Now, what is a normal structure? Normal structure means for all normal masonry, steel, and earth retaining structures that comes under normal structures. And important structures means the design standards for important buildings, bridges, and earthen structures. So critical structures means applied to the critical masonry, steel, and earth retaining structures. And special structures means bridges and earthen structures required the highest safety standards. So these there is a tabular column which is given in 1893. So based on the like what are the types of building that comes under each and every category of the structure, for normal to special structures. So this is for working stress method. So here there is one more concept called working stress method and limit state method. So which is based on the performance based design. The 1893 code, the current version of the 1893 code is based on the performance based design. So that's why these two methods are provided. So the draft code, if you observe 1893, so there are two terms called strength criteria and serviceability criteria. So similarly, here the terms are replaced with performance based design. So different. So if you see the limit state method, the for normal structure the written period is 900 and, sorry, 475 years. But whereas in a working stress method, the written period is 175 years for normal structures. So similarly, you see for special structures, the written period is 4,975 years. But for working stress method, the for written period for special
Sorry,
structure is,
sorry to interrupt.
yes.
We are not able to see your slides.
Unable to see, huh?
It was there just 1 minute before, it got.
Now is it okay moving?
No, no, we are not able to see the. I think screen sharing stopped.
Screen share, 1 second. Yeah, now is it visible?
Yes.
Yes, sir. Yes,
Is
sir.
it
It's
moving?
visible right now. Yes, yes.
Yeah, fine,
Yes,
thank
it's
you.
moving.
So now if you observe the return period for limited design, the maximum return period is 4,975 for special structures and for 975 years for the special structures in working stress method. Then the next parameter is the importance factor, as I discussed just now. The importance factor is used in the estimation of the design acceleration coefficient of a structure shall be taken as specified in the respective part of IS 1893 depending on the type of the structure. Now the categories are given like normal structure, important structure, critical structure and special structure as per the clause 8.2 of IS 1893 part 5. So the irrespective of the type of the structure, the importance factor is 1. So that means we are not considering the importance factor in the current version because 1 means anyway we will get the same value. Okay, but in the earlier version of the code, the importance factors are given like 1, 1.2 and 1.5. Next, the important parameter is the design spectrum. So earlier, the design spectrum is different, and here the design spectrum is completely different. So the site classes A and B, site class C, site class D. Actually, the site classes are categorized based on the shear wave velocity, that is VS30 value, and these VS30 depending on the VS30 values, the site classes are classified. So if the VS30 value is less than 180 meter per second, then the site class is categorized as E, and in between 180 to 180 to 360, it is given as a site class D. 360 to 760, site class C, and 760 to 1500 it is classified as B, and from less more than 1500 then it is classified as A. So based on that the site classes are given. And how do we calculate if the given site has say more layers, say 3 layers or 4 layers, then if that is the case, then how do you calculate the site class? So for that, the equations are given in IS 1893-2025 for calculating the VS30 value also. And based on that, based on the site classes, so we have to see the normalized design horizontal elastic pseudospectral acceleration for 5%. And remember, the spectrum which is given is only for 5%. And if the if we want more than 5% or more than 5% damping ratio, then what we should do? Okay, so for that also the code is given some recommendations. But in the earlier version, the factors are given only if the damping ratio more than 5% or less than 5%. And these are the equations to be used if the structure is above ground. So if the structure is above ground, then ANH for 5% damping ratio are calculated for various site classes. Site class A and B, it is given the equation. In between, if the fundamental time period is in between 0 to 0.4, 0.4 to 0.6, and 6 to 10 seconds. But for class, similarly for class site class C and site class D. And if yeah, anything you need? Some disturbance is coming. Yeah.
Chetan,
So coming to the design spectrum coefficient in vertical direction. So earlier it is given in horizontal direction, and this one is for vertical direction. Now for vertical direction, so we need to multiply the factors with delta V TV. So what is delta V TV? So delta V TV means the values are given for different, similar to the SA by G value. The values are given for various site classes. So if the vertical time period is in between 0 to 0.01, then we use delta V TV is 0.8, and this value is to be multiplied with these factors. So then only we'll obtain A in V, that is in vertical direction. But whereas in horizontal direction, we don't have any multiplication factor. Okay, so then what is the fundamental time period of the structure in vertical direction? Okay, so then like after so many debates in the committee, then it is given as 0.4 second, excuse me, so 0.4 second is given for the fundamental time period in vertical direction. So 0.4 second means it is in between, that is 0.1 more than 0.1 second. So that means we have to multiply 0.67, 0.67 and 0.67. So irrespective of the site classes, the delta V TV is taken as 0.67. Then, so when do we use these kind of fundamental periods in vertical direction? Means this is maybe for different kinds of structures, maybe pipelines, or there are other structures also. Okay, so for that kind of cases, so we use these time periods. Okay, so then the normalized horizontal and vertical pseudospectral velocity and the normalized horizontal and vertical spectral displacement. Now, the equations which are given here is for acceleration. So these are the horizontal direction acceleration, vertical direction acceleration. Okay. Next one is, so how do we calculate the horizontal and vertical pseudospectral velocity and spectral displacements? So for that, the equation is given, that is whatever the value that you calculated, to obtain the velocity factor, the velocity component, you have to multiply with th by 2 pi. And if you want to calculate the displacement value, you have to multiply with th by 2 pi whole square. Okay, so these are the equations given in 1893. Then, so the equations which I discussed so far related to the design spectra are if the structure is above the ground. Now, what happens if the structure is below the ground? Now, there are like in metro areas like Mumbai, Chennai, or maybe Hyderabad. So, some part of the structure is below the ground and some part of the structure is above the ground. So, if that is the case, then how do you consider the structure below the ground? So, for that, for the structure or the portions of the structure buried below ground by the drilled in place construction method, the normalized horizontal and vertical below ground shall be estimated using these equations. So that means if the height of the structure HE is the height of the structure here. So if the structure is like in between 0 to 30 meters, then for horizontal coefficient value, we have to use this equation, and if it is more than 30 meters, simply multiply with 0.5 with the calculated ANH earlier. That means 50% you have to consider the as a below the ground. Now, in the drilled in place method of the construction, this reduction shall be considered in the earthquake analysis of such structures only by equivalent static method and not for response vector method. This is very, very important. Equivalent static method, and it is not considered for the response vector method. So this reduction shall not consider in the cut and fill method of construction below the ground. And here, if you see the spectrum here for site class A and B, C and D, but what about site class E? So basically, it is categorized as a site class A to site class E, but the spectrum is not given for site class E. So for that kind of case, then we have to go with the site specific hazard analysis. Okay, so wherever you are going to generate the spectrum, so for that particular site. So, for example, for Mumbai region, I want to like consider the site class E where the like VS30 value is less than 180 meter per second. So if that is the case, for that particular location, one has to generate the ground motions, and based on that ground motions, generate the spectrum, and that spectrum we have to use in the analysis. And there, z component is not there in the equation. If you observe the equation which I have given here, yeah. So here, so there is a z term here for calculating the design base shear in horizontal and vertical direction. But there, for site class E, there is no z component here, because the one has to generate the ground motion and the spectrum itself. So there is no z component. So it is already embedded in the spectrum itself. So that's why z component, it should not be there for both horizontal and vertical directions. Then the next one is the normalized horizontal and vertical below ground is similar to the earlier case. Next, so if the damping ratio is like other than 5% of the critical damping, so far we discussed about if the damping ratio is 5%. Now the case, you have to multiply with a factor, that is delta zeta, in for both horizontal and vertical directions. Okay. So what is delta zeta value? The equations are given here. So like if the horizontal fundamental period is in between 0 to 0.01 second, 0.01 to 0.1, and 0.1 more than 0.1, and in between TAV to 6 seconds. Now what is this TAV for all these cases? So if you observe the design spectrum here, the design spectrum here, so the values are given 0.4 and 0.6 and 0.8. So this is the corner period of the structure. TAV is the corner period of the structure. So if you observe the design spectrum, so initially at 2.5, it is a like constant with respect to the time period. So up to 0 to 0.4 seconds, it is a constant for site class A and B, and after that reduction takes place with respect to the natural period. So that is your TAV for site class A and B. For site class B, the TAV value is 0.6. For site class D, the TAV is 0.8 seconds. Okay. So though for if your time period is in between 0.4 to 0.6, then we have to use this equation. So like that it is categorized. So that is what is the corner period, as I discussed, and in that there is a term called eta max zeta. So the eta max zeta value is given for if the zeta value is 0, we use 3.2 as a eta max zeta value. And if it is in between 0 to 0.005, that means 5% damping ratio, and 5% to like sorry, zero point 0.5, and zero point 0.5 to 5%, we use this equation, and 0.5% to 30%, we use this equation. And here there is no guideline or there is no clause if the structure is more than 30% damping ratio. So there is no expression given in the code for eta max zeta for values of zeta more than 30% of the critical damping. When such kind of situation, then whatever the value that you obtain for 30% value, that is eta max zeta value, we use the same equation if the zeta value is more than 30%. Yeah, so this is what is the site classification, site classes for how to calculate the site classes based on the shear wave velocity. So here, this is how it looks like the structure, like the profile of the soil. So for different layers, so you see different colors are given. Say, let us say the first one is a layer 1, layer 2, layer 3, and layer 4. So beside that, the diagram which shows the shear wave distribution of the shear wave velocity along the depth of the site. So from 0 to 100 meters, the depth is the shear wave velocity values are given. Okay, the profile is like this, in this manner. Okay, so based on that, so we have to calculate the VS30 value. So if it is only 1 layer, we can directly extract that value. But if you have say 4 or 5 layers involved in that, then we have to use this equation where T is the thickness of the layer, so that anyway we'll get that. And VS30 value, so VSI means that's the VS30 value, shear wave velocity value. So for different layers, so you have to take the summation of all the values and the summation of the thickness values. The ratio of the thickness to the TI by VS, then we'll get the VS value. So this is the classification that I already discussed for estimating the site classes. And the next is the shear velocity of each layer at the site of for normal structures in all earthquake zones. Important structures in earthquake zones 2 and 3 may be estimated by using the following approximate correlations. So there are equations that are given. So suppose for a given site I don't have any like shear wave velocity value in that particular area, but I know the n value, that is SPT value. So I know the SPT value. So depending on the type of the soil, that is a fineness content. So here the equations are given. So based on these equations, so I can easily estimate the shear wave velocity value. So like correlations are given based on VS30 and shear wave velocity value. So this kind of relations are there even in some of the PhD theses. Like for a Delhi region, Professor Nilma has used the shear wave velocity. Shear wave velocity for different regions in the Delhi based on the SPT values only. Okay, so like that we can extract or we can calculate or we can compute the shear wave velocity based on the SPT values. And coming to the approximate fundamental natural period, the approximate fundamental natural period translation natural period T of the oscillation less than 50 meters. This is very very important. If the structure is the height of the structure is less than 50 meters, then we use the equivalent static method. So if the height is more than 50 meters, then the fundamental period is to be calculated using IS 16700, which is based on the high-rise buildings. So if it is less than 50 meters, then we use the IS 1893 code. Okay. So for bare frame, where you have no infields, then the natural period, fundamental natural period TA is equal to 0.075 h to the power of 0.75 for RC structures. For steel, 0.085 h to the power of 0.75 for steel. So for bare frame, there is no change in the previous code and the current code. But whereas for RC buildings, the equation you have both denominator and numerator and denominator. But for numerator, if you have the 0.075 h to the power of 0.75, you already know this equation. But the denominator, which involves various parameters like density value or maybe is floor area ratio, that kind of thing are involved in this equation. Okay, so you have to calculate each one of the parameters and obtain the fundamental period value. For all other structures, the equation for fundamental natural period is 0.09 h divided by root t. Next, elastic force reduction factor, that is R. The R value is given for various kinds of structures similar to the earlier code. So, a schematic diagram which represents the R value for various types of structures. Okay, so for frame-based systems, the R value, that is a steel and RC. For that is a special moment resisting frames, the R value is given 5. And steel based frames, the value of R is given in between 3 to 5, and ordinary moment resisting frames it is given like 3, and for wall based GA systems the it is given 5, and special RC steel walls the R is 5, and under reinforced masonry the R is 1.5 to 2.5. Then the elastic force reduction factor, in that these three things are very very important. One is ductility, overstrength, and redundancy. So what is ductility? The ability of the structure to undergo large deformation without significant loss in strength. So that is what is the ductility parameter. And overstrength means higher strength than assumed in design, provided a safety margin against collapse. So this is what is somehow related to the factor of safety. And redundancy is the multiple load paths reducing the impact of the local failures. So this comes under the redundancy. Now, if I consider the ductility, overstrength, and redundancy, these three parameters in a pictorial diagram, it is drawn like roof displacement versus load or base shear. So initially the curve is straight and that's in linear manner, and after that when it goes to non-linear, so these three parameters comes into picture. So the first one is the linear elastic response. That's the maximum linear elastic. So from maximum elastic to the Fi value, that's the maximum load capacity in the nonlinear portion. So this comes due to the ductility part, and from maximum load capacity to the load at the first yield, that is due to the redundancy, and from first yield to the design force, that comes under due to the overstrength. Okay, and the response reduction factor is calculated as a maximum elastic force to the design force. So that means the ratio of this and this, it gives the response reduction factor. Then the seismic weight calculation, how we calculate the seismic weight. So the seismic weight of the structure is the sum of the seismic weight of all floors of the structure. Now, how do we calculate the seismic weight of each floor? Then the sum of the dead loads and the floor appropriate contributions of the weights of columns, walls, and any other whatever the loads that are there on the floor. So we consider all the floors from each and every story, and we take the half portion of the story below and half the story above, we consider as a seismic weight of the particle. Okay, so in that way we calculate the seismic weight, and summation of all the seismic weights for each and every floor, it gives the seismic weight of the structure. Then we use the same equation, and here the limits are defined for the design horizontal base shear for buildings of height less than, again it is given uh, height is less than 50 meters. The design horizontal earthquake base shear and VBDH for design shall not be taken less than. So this one is the minimum base shear value. So whatever the base shear value that we calculated, so whether the base shear is correct or wrong. So for that it should be minimum value, it should be ensured by the code. So that is 0.625 Zi by R into W, and which is greater than or equal to 0.015 W. And after obtaining the base shear value, so that base shear is to be distributed onto the each and every floor. The same equation is used for both the codes, that is 1893, 2016, and 2025 is the same equation. And these are the distribution distributed to the vertical members. So for in horizontal direction, if the flows are in rigid horizontal diaphragm action, then the distribution is based on the lateral stiffness. And if the flows are not in the rigid diaphragm action, then we use for based on the masses, that is from the tributary areas. And in vertical direction, it is getting distributed according to the axial stiffness. So this is what is the distribution of the base shear onto each and every floor. So this is how we calculate the design base shear and the distribution of the forces using equivalent static method. And this presentation is dedicated to the professionals and researchers contributing to the refinement, interpretation, and implementation of IS 1893-2025 for improved seismic safety of Indian built environment. And if you permit me 2 minutes of time, then I show one calculator which was developed by us.
Sure.
Yeah, so actually the IS 1893 2025 seismic base shear calculator. So the small calculator is like developed by Vishali Kamlakar, and we have both have written a paper on the evolution of the base shear from IS 1893 since 2000, since 1966. So how the base year is getting evolved from 66, that is from first revision onwards to till seventh revision of IS 1893. So still it is under our the paper is under review, and based on those calculations, we have developed this calculator. So if you see the earthquake zone, so the zones are defined here. So zone 2, 3, 4, 5, and 6. So earlier the zone IS 1893, earlier we have only four zones, 2, 3, 4, and 5. And the sixth zone is introduced in this current version. So similarly for written periods also, 75 to till 9975. So we have incorporated all the written periods, and importance factor anyway it is default, the value is 1 for 2025, and we are planning the same code is for various versions also. And important response reduction factor, so based on the type of the structure, this response reduction factor can be given. And site classes A, because according to 2025 the site classes are A and B, C and D only. And seismic weight, after you calculate the seismic weight, you have to given this seismic weight here, and the total height of the structure. And remember, the height of the structure, it should not cross 50 meters. And plan dimensions like horizontal direction, and in the other direction, that is length and width of the plan of the structure. And the vertical time period, anyway the value is default, it is given. If you calculate the base shear value, then in TX direction, what's the time period in X direction, time period in Y direction, base shear. Because as the time periods are change, as the time periods vary, so we have base shears in horizontal, that is in X direction, and Y direction also. Here Y is not in vertical direction, Z, Z as a vertical direction, and the VB, that is the vertical base shear value. So like that the values are computed. And the similar kind of calculations, there is a video in on my YouTube channel. So those who are not visited the YouTube channel, just the channel name is Acharya Gurukulam. Just you go and subscribe. There are a lot of videos that are available related to the IS 1893 codal provisions. And the whatever the lecture that I have given, similar lecture is there in the YouTube channel. And the one calculation, one building we considered and calculated based on the IS 1893 2023 draft code. And now we are planning to calculate the design wheel shear and the distribution of the shear as per the current code, that is IS 1893 2025, by considering all the aspects. Thank you for giving me the opportunity from the college. So if you have any questions, so you can ask.
Yeah, thank you, Professor Rajaram. It was excellent session with lots of knowledge for us, and our UG PG students, some professionals are also there. I see that Darpita, are you there? Okay, so sorry for initial glitch from my side. I couldn't hear a voice, and there was some miscommunication. So I see one question in the chat box. Given
Yes,
all
yes,
the
that
conditions,
I'm reading.
yeah, please,
Oh,
yeah.
yes, somebody typed what about the load combination. So that's why I told you when we're considering the equivalent static analysis, so we have to consider the load combinations also. But here the load combination is not discussed in my presentation. Okay. And one of the question raised by Ajit, given all the conditions are constant, how much percentage of increase in the base shear force value can be expected for the important structure located in zone 6 for LSM? Yeah, one second. So let me share my screen. Yeah, now you see here, base shear, yes, yes. So here you see, are you able to see this diagram? So actually, like at the end of the presentation, I told you, na, the we have written a paper. So in that paper, one of the result is this. So for Zone 6, as you asked, for LSM, you see, so there is a tremendous increase in the base share. So you see, I'll zoom it. So you see, from 800. Yeah. So from 600 for Zone 5 if you consider, because Zone 6 it was recently introduced for Zone 5 if you consider. So from 2016 revision to LSM. So this is the LSM value. So the value is around 1100. So almost double. 1600. So this one is around if you consider say 1100. So almost 1.8 times to 2 times the base share value is getting increased. This is for G plus 3 building. So like that, we have considered G plus 6, G plus 3, G plus 9, and G plus 15. So these are the three cases that we considered. So and the results are given here. Anyway, once we'll publish this paper, we'll share in the group so that you will get an idea of the evolution of the base share with respect to the zones and with respect to the revisions. Below ground and above ground seismic forces, and do we need to add them for the total combined effect? So actually we are like a video is it is in the process actually. So we are preparing a video related to this so that you will get an idea of how to calculate the below ground and above ground for the same structure. So if the structure is, some part of the structure is below the ground and some part of the structure is above the ground, then how we calculate the base share. So actually we are in the process of preparing the video. So just I'm just typing the name of the channel here. Acharya Gurukulam. Yeah, any other further questions?
I wanted to ask, now I have UG PG students with me and they use it as
Hmm.
SAP. So how this it will be integrated? Means still it is IS 1883 2016 only being used, na? So how do we see that? I mean,
Yes,
should
yes,
we?
sir.
Yeah, please help. Can you guide us on that?
No, no, actually 2016, most of the softwares are embedded in 2016 only. So for getting 2025, the revision of this code into the softwares, it takes time. So meanwhile, like one has to use either maybe Excel sheets or maybe some kind of programming for their analysis and design of the structures. So because they don't have any other choice, no. So once it is integrated in the software, so then only we can use. So till that time, either you use like previous version of the code, that is 2016, or if you really want to implement 2025, then you have to write your own program or check with the validation part and that kind of thing one has to do.
Okay, sir. Thank you.
Yeah.
So, sir,
Yes.
what inspires you to choose this field and what keeps you motivated till today?
Yeah, you can ask Archana ji.
Yeah, she's my UG student. So
Yes, yes.
she is really interested to know. You can really tell about yourself so that students are also aware
Yeah,
about.
Darpita ji, you can discuss with Archana ji, so she can explain very well. Okay.
Okay, bye.
Yeah, you can contact me also. So my number is also displayed here. So you can contact me at any time. First, just you introduce yourself. Like whenever I am free, I'll give the appointment. So we'll discuss regarding the portal provisions, and so whatever the content that are given in my channel is divided into three parts. One is machine learning related to the civil engineering applications, and second one construction practices. Third one is the about codal provisions. So, what is the background of the codal provisions that are given in the channel?
Okay, sir.
Yeah, this one. Somebody posted. Yeah, the same exact link. So just to follow the channel so that you will get a lot of knowledge related to the codal provisions and construction practices. And nowadays students are very much passionate about the machine learning also. So those kind of things, how we calculate manually. So if you solve an example problem, then you will learn a lot of things during that calculation. Okay, so those kind of things, how we calculate each one of them, that will be discussed in the channel. So that will be useful for your projects also, for UG and even PG also. I can say even for PhD students. Yeah, any further questions to be asked? Tell us that how will work. Yeah, how how will work on ETAP software as per. No, no, revised course, there should be some kind of research and development it will be there in each and every software company, like civil related software companies. So once it is the values are validated, so then only it will be integrated in the softwares. So right now we don't have any other option. Either you use 2016 code, or if you really want to use 2025, then for your building you have to write your own program, or whatever the distribution of the lateral forces that you calculated for different combinations. So those values to be included as a lateral loads onto the structure. So that's what we can do using either EDAPS or SAP or whatever the software, because the software will not directly calculate the lateral loads. So you have to give as a lateral load. So now the calculations, the lateral load calculations, you calculate manually, and those values you have to given as a lateral load onto the structure. Any further questions?
I think there are no more questions. So I think we can end the session if there are no more questions, and there are requesting Darpita. So kindly press the code of thanks.
Yeah. On behalf of organizing team, I extend our sincere gratitude to our self-esteemed speaker, Dr. Chena Rajaram sir, for sharing valuable insights and making this online session informative and engaging. We truly appreciate the time and efforts taken to be with us today. I would also like to thank you all participants for joining the session and for active involvement despite the virtual format. Your presence and interaction made the session meaningful. My heartfelt thanks to the organizing team and technical support members for ensuring smooth and successful online experience. Once again, thank you all for being the part of the session. Thank you.
Thank you, Archana ji, for sharing the this one. Okay. Thank you, one and all.
Thank you so much.
Yeah, yeah,
Yeah,
yeah. We'll discuss over the phone. Meanwhile.
sure, sure, and we'll again invite you for future sessions. Thanks a lot.
Sure, 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 sure. Huh? Okay, yeah, yeah.